mix of people, so I wanted to talk a little bit about p-Adic aspects of Maass forms in various incarnations, and in particular maybe advertise and further explore some analogies that were proposed by Don Blasius and Frank Caligari a number of years ago, and explore sort of how this goes. And so my goal today, quite simply put, it's to explore an analogy that's perhaps not all that well known, but is very compelling. It was proposed by Blasius and Caligari, as I said, so explore analogies between two sets of spaces. The first is the space of Maass forms, which already this morning made an appearance in Sandro's talk. So this will be the story that corresponds to analytic modular forms at the infinite place. I want to contrast that with certain properties that they share with the theory of overconvergent eigenforms, which will really be the analytic theory of modular forms at a finite place. And then there's many ways that you could explore such an analogy. You could take virtually any property that you might care about for Maass forms and see if there's a compelling analogous story on the p-Adic side. But I'll focus in particular on two themes, which I'll try and explain with a sort of small caricature on this board. So let me start with a board that explores a little bit the story at the infinite prime, which will be very well known to many of you. So here the story is that I want to consider the action of the hyperbolic Laplacian in weight k, which we also saw appear this morning a space which you might call M infinity of Maass forms, precisely as defined this morning, so I won't repeat the definition. So Maass forms of weight k. So I'll be interested in particular in the spectrum and the eigenforms for certain eigenvalues for this hyperbolic Laplacian. So let me draw a small sort of cartoon picture to put into contrast with the non-Archimedean story that I'm about to tell you in a second. So the spectrum consists of all the eigenvalues of this Laplacian. We might choose to visualize sort of on the line. They're all real numbers. The eigenvalue 0 might play a particular role, and then perhaps we have some big gap depending. So for the talk of today, I'll just be in level 1, so SL2Z, but really nothing changes with higher level, just to keep it as concrete as simple as possible. I can also choose a weight, of course. Maybe the weight is 0, and in that case I get a bunch of other eigenvalues. If the weight was indeed 0, the first one occurs after a gap, it's like 90 point something. And then maybe there's other eigenvalues that are somewhat scattered on the real line, but otherwise very difficult to get your hands on. So they're not algebraic, they're expected to be transcendental numbers, and we don't know too much about it. So this is the picture, I guess, for k is equal 0. But we do know roughly how they're distributed. So we have a Weil law for these eigenvalues, which has been known for a very long time. So asymptotically, we understand roughly how they're distributed. And then here we have the space of harmonic Maass forms, where we might expect to see, maybe not in k is equal to 0, but we might expect to see some classical modular forms, which this morning were called holomorphic modular forms. On the p-Adic side, that's more common to call them classical. And so much of my work, maybe in recent years, has been in this spot. So I'll say maybe a couple of words, but today I want to talk about the rest of the spectrum. So we might see some classical forms, which of course I don't have to convince you are interesting modular forms to consider, holomorphic ones. And then maybe in recent years also the theory of weak harmonic Maass forms. Can be found in this part of the spectrum, except to see those we have to weaken the growth condition at infinity. So this weakening here we might also look for on the p-Adic side, and I'll tell you a little bit about how that goes in a second. And this theory, of course, has been has led to lots of arithmetic applications, but I'd like to single out two that have been important for my own work. Oops, applicants and applications.
Maybe swap the boards for the benefit of those who sit in the back row.
Oh, sorry, yes, absolutely. Can I maybe finish writing the names and then I'll swap it, yeah, because I'm almost done with this board, and then it'll be up and ready for everyone to see. So I'd like to single out, I mean, I could name many people, but certainly the papers of Brunier and Vonk, as well as the paper of Duke and Lee, were a very important inspiration for what I'll put next to it on the p-Adic side in a second. So I'll flip the boards, so hopefully this is a bit more. Okay, so it's my cartoon drawing of where we stand. So I won't talk about this part of the spectrum today, even though that has led to very concrete arithmetic applications. I would like to focus on the more speculative side of what happens with the higher eigenvalues. Okay, so let me try and draw a picture here now at a non-Archimedean place. So I'd like to consider a theory of analytic modular forms, but p-Adic analytic modular forms. And so, as proposed by Blasius and Caligari, a compelling analogy can be made between this setup and the setup where I consider the action of what's sometimes called the Atkin operator. But it's just the operator UP, which takes modular forms that have a Q expansion A and Q to the n to A and P Q to the n. So I want to consider the action of this space, which of course they act on modular forms of level gamma 0 of P, if you will, but they will also act on the space, which I might call MP of overconvergent modular form. So let me draw a little asterisk here, because I'd like to give you, at least for those of you who haven't seen the definition, a quick definition on the other board before I return to this board and draw the spectrum. So let me flip the boards here. And tell you sort of a simple way of thinking of this space. Typically defined to be the sections of a line bundle omega to the tensor power k, and I didn't say actually what the weight is. The weight is integer. Let me add that, since that's not a given for many of you. I will take an integer weight, and I will do the same here, so at least this makes sense. But now I want to tinker with this a little bit, because if x is just the modular curve of level 1, this would be classical weight k forms. But what I would like to do is I would like to take a weakening that's maybe similar to the weakening that we do when we consider mass forms from holomorphic to real analytic. That's an analytic weakening which p-Adically is difficult to make, and the theory of p-Adic analytic functions is typically closer to the theory of holomorphic functions than its real analytic counterpart. So the weakening that we put in here is a weakening where we don't ask for our sections to converge everywhere on the modular curve. In fact, we ask for them to converge on some p-Adic aphanoid subset inside of it, which concretely is constructed as follows. So suppose that this is my modular curve, x of 1, considered over the field Cp. Then what I can do is I can take Cp points of this curve and reduce them modulo p. And likewise, a picture of the modular curve mod p, which has a set of distinguished interesting points that are the supersingular points. In fact, maybe I've been given colored chalk, so I might as well use it. What's a good color for supersingular? Purple?
Yeah.
Red? Oh, red.
I was going to say purple.
Purple? Oh, okay. Well, who prefers purple? Yeah, who prefers red? Okay, sorry. Sorry, hold on. Purple it is. So these are supersingular elliptic curves, finite in number. And if I look at all of the set of all the Cp points that reduce to it, then what I get is I get a certain disk, p-Adic disk, in the generic fiber, which I'll henceforth call a supersingular residue disk. And of course, what I'm doing here is I'm considering the reduction map from one to the other. Okay, now each disk what we could do is we could choose a parameter. It's a disk, so it's rigid analytically isomorphic to a disk by some isomorphism, so that's my choice of parameter. A. So that the equation of the disk will be consisting of a set of points where the absolute value, now p-Adically speaking, is less than or equal to 1. Now inside of this disk, I can take for any value of r that I like, say a rational number that's not too big, so close to 0, I could take the set of CP points where the value of my parameter is in fact bounded by p to the minus I. So geometrically what I'm doing is I'm looking at a smaller subdisk inside of here, where the radius of this disk is prescribed by the value of r. And what I can do now is I can take away these open disks and just say xr now is the complement of these smaller disks. Right, so I'm taking away these smaller disks and I'm asking for my sections of my line bundle here to converge a little bit into the supersingular locus. And that little bit is prescribed by R. Yeah? So this is what I call an R over convergent form. And if I don't specify, and I just say over convergent form, I mean something that's R over convergent for some value of R. So take a big union of all of these spaces. Okay? Right, so this is a big infinite dimensional p-Adic space, but luckily this operator UP is compact, so there's a good spectral theory. And so I can flip the boards again, draw a picture of its spectrum. Good. And now there's one passage that is maybe slightly mysterious. I will not draw a picture of the spectrum, but rather of the valuation of the spectrum. So these are typically called the slopes. That's a topic about which there's a vast literature, slopes of overconvergent modular form. And what these slopes are, so I had lambda here, that's the actual eigenvalue. The slope is not the actual eigenvalue, it's just a measure of the size of the eigenvalue. So it'll be the p-Adic valuation of the eigenvalue, the number of times it's divisible by p. These will always be integral, so 0 is the smallest value that you could possibly get. And then maybe there's the rest of the slope spectrum. So typically there's a bit of a gap, and then there's other slopes that occur here. And so maybe for the sake of concreteness, and I'm telling you a couple of numbers, let's take again k is equal to 0, and p is equal to 2. Yeah, there's always an additional choice now of a prime involved. For p is equal to 2, we know in fact the full set of slopes, and it's now by 0, 3, 7, 13, 17, etc. So for very different reasons, and not particularly to be made into analogy with the space of Maass forms, these slopes have been very intensely studied. One kind of striking thing about it is that they're integers in this case. And in fact, they will always be integers for this particular choice of parameters. That's not something that is true in general. You could get rational numbers also. But there is more of a discrete feeling to these slopes in general. The denominators of the slopes tend to be quite small. Okay, now here, this subspace, so that's the overconvergent forms with slope 0, they're often called the ordinary modular forms. And it's not really one-to-one, but you can think of these maybe as being somewhat close to the classical holomorphic modular forms on gamma 0p in that weight. So slope 0 in most positive weights will imply that you're automatically classical. And the converse is not true, but it's fine to think of it in this way. And then what seems to take the form in maybe some of my recent work of this analogy with the weak harmonic mass forms, the weakening is taken in the weight aspect. So you take typically p-Adic families of these, and you can take their first order deformations, and these deformations seem to play very much the same role as the weak harmonic mass forms on the other side. And so I'd just like to point out that there are also arithmetic applications of considering these objects. And maybe I should have talked about that, but I chose not to today. Applications. And so let me mention that I have joint work with Henri Darmon, and also another work with Alicia Tozzi, which explores this further. So this is all centered around this ordinary subspace of these overconvergent modular forms and deformations thereof. What we haven't touched is the rest of the spectrum. And that's what I want to talk about today. So Blasius and Caligari suggested that, in fact, there are many compelling analogies to make between the two sides of the picture. And in particular, they raised the question, which is confirmed by lots of experimental and theoretical evidence, that there might also be a Lie's law on this side. Even though we cannot prove it, we can prove certain weaker versions of it, and certainly numerically this seems to hold beautifully. And this is really suggested by Blasius and Caligari. So when it comes to the spectrum, there's a lot to be said about that, which I won't do today. I would like to focus today on some other aspects. I would like to look not just at the spectrum, but at the actual eigenfunctions. So the p-Adic analogues of the mass eigenforms corresponding to a certain eigenvalue of the Laplacian. So today, what I would like to explore with you is the question of how these eigenfunctions behave, not individually, but as the energy or the eigenvalue goes off to infinity. So here, of course, that's a well-studied topic, these high energy limits of mass forms and equidistribution of various things associated to them. Here it's maybe much less studied. It's one of the things that Caligari suggested should be studied. I want to consider limits as this slope goes to infinity. And I would also like to study the zeros of these overconvergent eigenforms, which again, in the case of mass forms, is a very well-studied problem, but a very hard problem also about which we can't yet say the final word. So let's do a little bit the plan. Now, the first thing I have to do today is to convince you that this analogy is a compelling one. And so the first thing, inevitably, is to compute some examples and to explore together with you what these examples look like. So if all went well, I've set up the computer here. It's a bit unfortunate now you can't see the backboard anymore. I'm sorry about that. And you can't see the screen either. That's because my computer is... Oh, so, and I should say that, I think I said it in the title, but everything is joint work with Paolo Borzini. Okay. So, like I said, we'll consider two things, these high energy limits, which will be my name for what happens to the eigenforms as the slope goes off to infinity, and then also their vanishing locus from the zero locus. And so we'll start with the high energy limits. Okay, the first thing to notice is that these limits exist as Q expansions and even as overconvergent modular forms in great generality. And in fact, p-Adically, you have benefits that you often don't have in the Archimedean world, where often you're sort of sentenced to using the trace formula quite extensively. Here we have other tools also that we can leverage to say something about these kinds of limits. And the first thing that I want to tell you is I want to tell you this lemma, whose proof is kind of soft and topological. And what it's saying is that if I look at the eigenforms here of increasing slope, and I take any sequence of such eigenforms, if all the eigenforms are defined over a fixed finite extension kp over qp, then there will always be a subsequence of them that converges to a limit. So in some sense, you can find lots of limits. You can take any subsequence of the eigenforms. As long as they're all defined over the same field, you will always find a convergent subsequence. So let me just, as an illustration of the kind of benefits that one has in the p-Adic world, tell you a little bit about the proof, even though it is kind of a soft fact, soft topological fact. So what we'll do is we consider the bad primes for the level structure, which for me was just SL2Z, so that's nothing, but then also P. And if I have some overconvergent eigenform, it has an associated Galois representation. And that's going to be very useful for us, because that associated Galois representation, it's a Galois representation unramified outside of the primes that are bad into GL2OP, where OP is the valuation ring of my finite extension over which everything is defined. I can always conjugate to land integrally inside of this Galois representation. Now, Serre's conjecture says that if I take this Galois representation and I reduce it modulo P, there's finitely many options. And there's finitely many so-called residual representations. So now what I can do is I can pass to a subsequence of forms that at least all look the same mod P. You know? And there's finitely many, and there's infinitely many of my forms, so such a subsequence must exist. Yeah? So I can assume rho bar is constant for this whole sequence. So now I can say, okay, well, these Galois representations, they're all lifts of this fixed mod P Galois representation. And all possible lifts are classified by some deformation ring, about which we know very nice properties. So, in fact, all lifts give rise to points on the scheme that classifies such deformations. It's a formal scheme associated to some framed deformation ring. It's a little bit technical, but this framed deformation ring always exists. And the point is that this is a compact space. So now I have infinitely many points in a compact space, and so there will be a convergent subsequence inside of it. Yeah. So such a point corresponds to, a point I'm just writing this out and what that means. So it corresponds to a point. This is finitely presented, and so therefore you always get an infinite set of points on a compact space has a convergent subsequence. So ultimately, the compactness of this deformation ring gives you this abundance of limits. So that's the first thing I want to tell you, that the mere existence of these limits, it has a lot of freedom. There's nothing too specific about the sequence that you take. But of course, we would like to say a little bit about what these limits look like more quantitatively. Can we describe the limits of convergent sequences of finite slope eigenforms that we get? And that's a little bit the mystery. So I think Caligari noticed also that these sequences exist, and in fact, there's one specific one that he wrote down and investigated, which I'll come to in my slide. But systematically, it wasn't so clear what all of these limits now particularly look like. So that's what I want to explore.
And may I ask, this convergence, what is it? Is it absolute convergent on a p-Adic space? What kind
Precisely.
of...
So on XR, for R at most 1 over P plus 1. That's the technical version we prove. But you can, for the purpose of this talk, it's also fine to think of just the Q expansions. If I look at the Q expansions of these forms, p-Adically they will converge to a limit, and this limit will still be an overconvergent.
Uniformly on all the coefficients?
Yes, the Fourier coefficients of the Fourier expansion. Exactly.
Uniformly?
Uniform, yes, absolutely. Uniform.
Okay.
Yeah, absolutely. Okay. All right, so that was the first thing we had to investigate. What do these limits look like? The fact that they exist is already kind of miraculous, but can we say anything more about it? So let's first do an example of such a sequence. And this one was noticed already by Caligari. So it's an example for the prime p is equal to 2. That's the smallest prime, so why not take that one and keep the computation somewhat manageable. There's another reason for choosing this one, is because we actually know already a lot about the slope sequence. It's this sequence that I wrote down in my example before. It's actually the unique slope sequence that we completely know. All the others we don't really know. Maybe we have some conjectures in some cases, but it's a very wild thing, this kind of spectrum of slopes. This is the unique case where we fully know what it is. In fact, Buzzard and Caligari showed that it's 1 plus twice the p-Adic valuation of 3n factorial over n factorial. Very bizarre. It's a miraculous result, and amazing that they were able to prove this by raw power somehow, and computing really what came out. But it's a very mysterious kind of sequence. Nonetheless, we know exactly what it is. And so what I've done here is I've put the slopes in boldface, and then the little subscript indicates the multiplicity. And so for Maass forms, we expect that the multiplicity should always be 1. For slopes, that is distinctly not true. It is true in this example, All the slopes occur with multiplicity 1. But in general, that is not true. And that comes from this discreteness that the slopes have. So if they're forced to be an integer, then sometimes they will coincide. So even though the eigenvalues might be different, the slopes might be the same. So the multiplicity is 1 here. That's another thing that makes it somewhat pleasant. And in fact, for our conjectures later, that will be a very, very useful feature. Okay, now what happens in this case? We can look at the eigenfunctions that have this slope, write them down as Q expansions, and there won't be any classical modular forms. This is in weight k equals 0. The only classical modular form is this guy. That's the constant function 1. And weight 0, that's the modular form. It's an eigenform, and it's ordinary. Yeah? So its UP eigenvalue is 1. Okay, so what we could do is we can now enumerate the eigenforms by slope. So the first one is just a constant function 1, and then all these other will be some non-classical, so non-holomorphic p-Adic modular forms. We can nonetheless compute them. And Caligari did exactly that, and in 2013 he observed numerically that there's this very bizarre continuity in the index set. So he writes down, or one can write down the function from n to z2 cube, our series over z2, that sends a natural number n to the nth eigenfunction, or its Q expansion. So for instance, the value of this function at 5 would be the Q expansion of this guy, the guy that has slope 17. Now, that appears to be continuous in n. Yeah? So when I put a p-Adic topology on n, in this case a 2-adic topology, and here I put the uniform topology on the Q expansion. That appears to be continuous experimentally. More specifically, if it appears to be continuous, then if I take the index set to be a power of 2, and I let that grow, then I expect maybe that thing might go to a limit. At least they become very congruent to each other, so it should go to a limit. And in fact, one observes that it converges to this limit. So this 2-depleted weight 0 Eisenstein series, which has a Q expansion, has this shape. So you take out all of the coefficients that are even, and then for the odd ones, you sum up the inverse of all the divisors of n. All right, it's an experimental observation. In fact, let me let you observe this observation. So what I've done here is I've computed the eigenfunctions fn, and I've made a table here, and these eigenfunctions here are counted 0, 1, 2, all the way up to 79. So I computed 79 of these eigenfunctions. And then the entry below measures how congruent this eigenform is to this limit. And how congruent means modulo 2 to some power, and that some power is in this table. So for instance here, this entry is telling me that the fifth eigenfunction is congruent modulo 2 to the 7 to this limit. So this is the table. Now I've suspiciously highlighted, first of all, there's a lot of congruences. Yeah, 7 seems to be the lowest that you could even get in this sequence, which is already striking. But there's one particular column, and that's the reason I cut off at 16, one particular column where the congruences are extremely high. So the 16th eigenform, the 32nd, the 48th, and the 64th are all extremely congruent to the limit, and that's what we're seeing here. And that's what Caligari, in fact, already saw many years ago. Okay, now this continuity, maybe this is a natural one to pick, but you could take other subsequences and likewise ask, what is this limit? Where does this 2-depleted weight 0 Eisenstein series come from? So we did more systematic computations with Paolo. And I want to show you some of these observations before, hopefully I'll have time to say something about a theorem that we can prove. There's first some experimental observations. So the first thing we're going to do is we're going to enumerate all the eigenforms, put them in a list like we just did, by increasing slope. Now I've put this in boldface because in general, we can't do that. Yeah, the multiplicity will be higher, so I don't know how to order them linearly. So that's an issue that will come up in general. But for nice examples like the one I just showed you, because of multiplicity 1, that does not happen, so we don't have to worry about that. So let's put ourselves in this setup. There's plenty of examples already in this setup. Now, what happens in this setup is really bizarre. It's the following. Take any integer. Let me call it big M. And now take a sequence of integers that goes to infinity in the real topology, so it becomes arbitrarily large. But in the p-Adic topology, it goes to my integer m that I picked. So the case that Caligari was exploring was m equal to 0. He was looking at the index set that converged to 0, but went off to infinity. But in fact, you could do this with any integer. And what we observe is that this sequence converges, and in fact, it converges to a very specific limit. Now, what is that limit? It's what I've called EP of G here. That limit is the Eichler integral of a certain, depending on m, and that's what I'm about to explore together with you, finite slope eigenform G of weight 2 minus k. So everything here has fixed weight. I fixed my weight from the beginning. Maybe in this example it was 0. There could be any integer that you like. I have an infinite set of slopes, but somehow these limits are governed by the modular forms in this kind of parent weight, which is 2 minus k. So I have two things to do. I have to tell you what the Eichler integral is, how it's defined, and I have to tell you how these certain finite slope eigenforms are defined. In fact, if all goes well, maybe we can discover it together based on the data in a second. Okay, so first I have to tell you what the Eichler integral of any form of weight 2 minus k is. As you might guess, if I take any overconvergent eigenform of weight k with q expansion a n q to the m, then I'm going to define its Eichler integral, and there's a dependence on p here, by just simply inverting theta k minus 1 times. Except if I do that and I introduce denominators at p, I'm just going to leave out those terms. So what I'm doing here is I'm throwing away all the Fourier coefficients that are divisible by p, and for all of the other ones, I do this formal inversion. So it's really a combination of what you, in the Archimedean side, would call the Eichler integral and a so-called p depletion, where you forget all the coefficients that are divisible by p. Okay, that's a definition that I'm making. Now, I claim that this is not just a formal Q expansion. This has a lot of structure. So, in fact, it's an overconvergent eigenform of weight 2 minus k. And this is only true if I do it, if I move between weights k and 2 minus k. If I formally invert any other power of theta, it will never be overconvergent. It will only be a p-Adic modular form. But these are overconvergent of weight 2 minus k. So they live in a bona fide other spaces and other weight. In fact, it's very overconvergent. It's R overconvergent for any R up to 1 over p plus 1. Yeah, so that's the cutoff. That's as far as this thing is allowed to converge, and it actually converges that far. Okay, and then the final thing is that it has infinite slope. So it's an eigenform for UP, but it's in the kernel. So it's one of these infinite slope forms. So in particular, if I do this to something in my picture here of weight 2, let's say, and I go to weight 0, I get something of infinite slope. So it's not going to be on my picture. It's somewhere all the way off at infinity. That's where this Eichler integral lives. But apparently, that's precisely the limit that I get for these convergent subsequences as the index set converges to an integer. So that's a very bizarre, mysterious feature. Okay. So just as an example, if I apply this procedure to the weight 2 Eisenstein series, then what I get is precisely this form that Caligari observed. Yeah? So it recovers, the construction recovers in particular that one example that we have. It's only one data point, so you could imagine making lots of other guesses, which we did, but the Eichler integrals are the ones that the computations really showed us. In fact, let me try and convince you of that. Okay, any questions about this before I show you an example?
E2, the classical E2 isn't modular, no?
That's correct. So there's several things to do. So first you can make it classical by taking its p stabilization, so viewing it on level gamma 0 of p, and just taking the divisors that are co-prime to p. Now it is classical, but the point is, whether I did that or not, the Q expansion will be the same. So it's a bit of a philosophical issue. If you're happier, you can write E2p, so the p stabilization, then it's just a classical form, and all is well. But indeed, it's a good form. So I snuck that one past you almost. Okay, so let's do it. So Caligari already noticed this example for the limit where m is equal to 0. So let's do the next one. And so let's revisit this setup. So this is k equal to 0. These are all the slopes that I get in k equal to 0. But now we're suspecting that the thing in the parent or the sister weight, I don't know what to call it, 2 minus k, has something to do with it as well. So we should also look at the slopes in weight 2, which look like this. So already there's a lot of patterns in here that if you take this sequence, maybe you leave off the first one, but you take this sequence, those are all the cuspidal ones, and you add 1, you get the sequence below it. That's not coincidence, that's actually what the theta operator shows you. Or you could just compute it and this is what you get. Yeah? So as before, I'm going to list my eigenforms here. I call them F0, F1, F2, all the way up to F5. They correspond to those slopes. And before, what Caligari was doing is he was taking this form, or that's our interpretation of what he was doing. He was computing the Eichler integral to this weight 0, 2 depleted Eisenstein series, and then he was finding a limit I converged to it. And the limit was the 0th, the 2nd, the 4th, the 8th, the 16th, and so forth. Converged to 0. Now I'm going to take the next one. I'm going to take this other form. By the way, this form, that's E2P. Yeah? That's a classical modular form. The next one is not a classical modular form. This is like a genuine p-Adic mass form. It doesn't have any algebraicity properties, and it just has p-Adic numbers as coefficients. But you can compute them to some precision. 2 to the 15th is what I've computed here. And I get this Q expansion. So these coefficients are presumably all transcendental, except the first one, of course. Okay, so that's what G of Q is. I'm going to do my recipe now. I'm going to compute the Eichler integral to weight 0. And I'm going to measure the congruences between my eigenfunctions and that Eichler integral of this form, which is a different form. So I don't expect the 0, 16, 32, etc. to be congruent to it anymore. They were congruent to another guy. Now I'm seeing lots of congruences in this column and in this column. In other words, the high congruences seem to happen whenever my index set approaches either 1 or minus 1. Okay, well, let's see if our luck persists and if this pattern continues. So let's do another example, and let's stick with the same setup, and let's just take the next one. The next form has slope 8, yeah? So that means it's U2 eigenvalues divisible by 2 to the 8. Let's call it G. Here it is, in case you wanted to see it. Modulo 2 to the 15. Now I'm going to compute the Eichler integral and measure the congruences again with all of my eigenforms. And now, lo and behold, I get high congruences, so 13, 14, 13, 15, etc., in this column and in this column. So in other words, when the index set is highly congruent to either 2 or minus 2. Yeah? And by this point, you can probably guess what the pattern is going to be in general. And if I take the mth one, then the limit had better approach m or minus m. And there's this additional symmetry with m and minus m that's actually quite interesting, and I hope to explain in the next example. Now, this is all data. I mean, we knew where we were headed, so we were looking at these congruences and focused on this, but at this point, if I throw this data, you might well notice something else. It seems to be full of patterns, this whole thing, and so there's almost more to conjecture than you have eyes to look. But this is a particularly interesting aspect, I think. Now, it's very difficult to prove any of this because of these overconvergent eigenforms, just like a mass form in general. It's very hard to say something about it. So you have to get your hands on these. So these are all experimental observations for now. Okay, so let's go back to this business of 2 and minus 2. And I just want to tell you what in general one might conjecture. And in fact, you might even conjecture it before I have time to tell you what the conjecture is. I want to show you an example that's a bit more genuine in the sense that it approximates the general case a little bit better. Yeah, so let's take the prime 3, and let's now go to some higher weight. And in fact, because everyone likes the Ramanujan delta form, let's pick that one. Why not? Yeah, so it's a weight 12 form, a full level SL2Z. Now, as you remarked before, to make this is full level SL2Z, so it's an eigenvalue for T3, the Hecke operator T3. But I need an eigenform for U3. Yeah? So I'm going to p-stabilize it. I'm going to take the old forms that are U3 eigenforms, and there's two choices, yeah? And they have slopes 2 and 9. Yeah? The slopes will always add up to 11, which is the weight minus 1. So they have slopes 2 and 9. So I can choose which one I take. I take that 3-adic stabilization, and as we noticed before, this process of computing the Eichler integral doesn't care which of the two I picked. The Eichler integral is the same because I'm going to p-deplete. And that's the reason for this symmetry between minus 2 and 2, etc. There's always two choices, and these are the two choices here. Okay, so the U3 slopes I've now put in sequences here for you, and I put a lot of colors, etc. So let's try and unpack it. So I'm in weight 12 here. The G that I'm going to pick is in weight 12. It's one of these two stabilizations, so it's either this one or this one. Okay. Don't worry about the numbering lower here. I'm going to try and justify that to you in a second. The upper numbering is the same, so F0 all the way up to F infinity. I list by increasing slope. There is still multiplicity 1 here, so that's good. Don't have to worry about this being well defined. Now, in weight minus 10, there isn't a single classical modular form. There's no modular forms of negative weight. So all of these are genuine p-Adic mass forms, if you will. Whereas in weight 12, of course, there are some holomorphic ones. There are some classical ones. In fact, there's 5 of them precisely. There's 2 Eisenstein series coming from the stabilization of the weight 12 Eisenstein series in this case. They have slopes 0 and 11. This is the ordinary Eisenstein series. This is sometimes what we call in the p-Adic the evil Eisenstein series, or the evil twin of this one. So they come in a pair, these two come in a pair, and this one is an new form. It's a new form of level gamma 03 and weight 12. That slope is always 5 in this case. Okay, so these are classical modular forms. These are not. In fact, all of these are in the image of the theta operator of something in weight minus 10. And you'll notice that all of these numbers are obtained from these numbers by adding 11 to it. So the theta operator has image all of these non-classical guys. But what we're doing is we're saying these are not in the image of theta. In fact, that's what characterizes them. That's what Coleman used for his classicality theorem. But never mind that, just invert theta anyways, and we can still approximate it by the sequence of finite slope eigenforms. That's kind of what we're saying. Okay, so this is another layer that you didn't see in the previous example, is that I'm supposed to twist my eigenforms also. So I take these eigenforms. For p is equal to 2, I didn't see this. But here, I'm supposed to take my eigenform and twist it by the power of the Teichmüller character that is the index of the eigenform. Yeah? Now, the Teichmüller character will just measure the nth coefficient, what it is mod p, and then depending on what that is, it returns a root of unity that you're supposed to put in front. So for 3, that's just putting a minus in front of the coefficients that are 2 mod 3, and otherwise just leaving the coefficient.
So your older guy in the slide should be from FP or from FP star?
Star, sorry, yes.
Yeah.
Thank you. FP. You can extend it, but then it's not a character. Well, but then it won't land in ZP star. You can just send it to 0 or something. But yes, absolutely, FP star. Thank you. All right, so here are the congruences. I take the 3-adic Eichler integral of my Ramanujan form, and I measure the congruences with these eigenforms. And here are the high congruences in columns. This one, and then also this one and this one. So at this point, I think you can sort of make the conjecture yourself almost, because what have we done here? If I label the classical ones separately from the non-classical ones, and I start with 1 for the first one that's really non-classical, and then I just continue counting negatively for my classical forms, then what seems to be happening is that if I go to minus 1, 3-adically, I converge to the Eichler integral of this guy. That's, for instance, what this column is. They're all congruent to minus 1. Whereas if I converge to minus 3, then I'm going to see these other congruences, which is what this column is. So these are congruent to minus 1 and minus 3. So again, we get the same kind of phenomenon as before. The congruences are a bit less high, but that's because I cut off at 89, and of course, 3 to some power grows very quickly. So if you increase the prime, you will see fewer congruences. You have to compute further and further, which becomes quite difficult. All right. Okay, so with that said, I think there's a lot of nice observations to make, but much to my frustration, it's very difficult to prove much about this. Yeah, you can try and prove, for instance, that there is some sequence of finite slope eigenforms that converges to these Eichler integrals. That's something. But it's very hard to say anything about this subsequence because it's hard to get your hands on these individual eigenforms. So for now, this remains an experimental observation. But maybe let's try and pick out something that we can at least try and prove. And that something is about the vanishing locus. So I have my eigenforms, and so I can ask, where are they equal to 0? So on the Archimedean side, that's a question that you will see before. So you have these beautiful visualizations. Many people do them, but originally I think Heyhal and Rechner were some of the first people to do this. If you take a Maass form, a non-classical Maass form, it's a smooth function, its 0 locus will be some real one-dimensional locus inside of the hyperbolic plane. And so here are a couple of examples. So this is the spectral parameter, so you have to square it and add a quarter to get the actual eigenvalues. And these are quite big already, these eigenvalues. And you see these beautiful kind of 0 loci as one-dimensional real subsets of the upper half plane. So this is something that people have studied a lot. So the components that you get for the complement of where you take these 0 sets away, they're often called nodal domains. And people have studied, for instance, how many nodal domains there are, whether the 0 locus sort of equidistributes on the hyperbolic plane, etc. So I'll just single out 2 things. So as far as I know, this is open, so there's a conjecture that says how many nodal domains there should be. It's the Bogomolny-Schmidt conjecture, which as far as I know is open, but we do have a very general bound of Courant, which just really applies to way more general manifolds, not just to modular curves. But that general Courant bound would show that the number of nodal domains is at most n. Yeah? But more specifically, asymptotically, we expect this more precise number. But we can't prove it as far as I know. One other thing we can ask is whether the zero locus equidistributes as the energy goes off to infinity. Yeah? And that's a little bit what this picture maybe suggests. You get a vague sense that the zero locus tends to equidistribute. There's no region of the modular curve that seems to be favored over any other. So you might conjecture that this is indeed the case. I don't think we know this. For holomorphic forms, we know much more. There's, of course, work of many people, but maybe the most general version, most recent, was by Rudin. So this is shown for holomorphic modular forms, where in that case, we're just looking at the number of zeros, of course, in the upper half. Yeah? The zero set. Okay, so let's go to the p-Adic side and see if this problem is more or less tractable than the infinite side. And let's again return to our trusted example from before, where we know all the slopes. We're happy to compute lots of examples just to get a sense of where the zeros lie. Now, here you can actually prove that the nth eigenfunction has precisely n zeros on this overconvergent region. So that means the ordinary locus and also the purple part of these. As far as it takes, as far as it converges, it has precisely n zeros. So the Courant bound is actually an equality in this case. That's quite amusing. But where are these zeros? This we still have to check experimentally. So any cusp form, of course, vanishes at the cusp. Yeah? I'm in weight k equals 0, so I'm really talking about functions here. It's extra convenient. And for the other zeros, what I've done here is I've listed again the index set of the eigenform, and then I've listed roughly where the zero lies. Now, what this is it's the value of r for which this zero occurs, where 0 means, so if r is equal to 0, that means that this zero of the modular form lies somewhere in the ordinary locus. Otherwise, if r is some rational number, it measures how deep into this disk this zero actually lies. Yeah? Where the maximal depth of this zero is taken up to 1 over p plus 1, which in this case is 1/3. That's sort of roughly where it starts cutting off, even though these things actually converge a little bit further. Those are all the zeros that we'll be interested in. So what we see here is we systematically get 1 0 at the cusp infinity, as we were expecting, and then we get all these other zeros that lie deeper and deeper into the supersingular part of this modular curve. And you get more and more of them, because for n, a certain value, there's precisely n zero. So here you see, for instance, 1 0 at eigenvalue or at slope 0, 1 0 at slope 1/4, and 5 zeros at slope 1/3. So that adds up to 7 zeros precisely for the 7th eigenfunction. So that fits. Now, here again, you can see lots of patterns. In fact, if the index sets are close together, we already observed before that the forms are very congruent to each other. So their zero sets might also look very similar, and that's exactly what we're seeing here. And these rational numbers, I don't know if there's enough time to let you stare at it, but you can easily come up with a conjecture for what this value is of this r. For instance, let's focus on the case 2, 4, 8, 16. Yeah? If you look at this subsequence, you see a kind of a constancy occurring where the r's that you saw before are a subset of the new r's. You just get extra r's a little bit deeper into the modular curve. You can even come up with a formula, and so if you do that, that's actually what Caligari observed for his example. It seems that the zeros occur precisely in this, for these values of r, with the multiplicity that's also, of course, 2 to the k in this case. Yeah? That's a question that he raised, and so you can ask, can you say in general anything about the zero locus of these p-Adic overconvergent eigenforms? Okay, so I'll leave that on the board, and I'll tell you which theorem we proved, and so let me erase this because I'm about to draw a very similar picture. Because in fact we can prove this for any prime for the Eichler integrals of the weight 2 Eisenstein series, which is, this is an instance of. So let me tell you what our theorem says. So we will prove in particular this observation, but we will do it for any general prime. So we can ask, what is the zero locus of this Eichler integral EP for a general prime P of the weight 2 Eisenstein series, which I'll just remind you is just the sum of p does not divide n, q to the n, where here I take the sum of all divisors of n inverse. Okay. This form is 1 over p plus 1 over convergent. Now, luckily, we don't need to know that this is a limit of specific finite slope eigenforms, or we don't need to be able to prove any of these observations that we previously made. We can just take this as the starting point. It's also a natural question. We take the Eichler integral of the weight 2 Eisenstein series p-Adically. What is the zero locus? Yeah? Okay, so here's our theorem. The theorem is that this regularity that Caligari observed really persists in full generality, and in fact, it also persists across the supersingular residue disks, which is something you don't see here because there's a unique supersingular residue disk in this example. Okay, so the theorem says P is a prime, and let me take D to be a supersingular residue disk on x of 1, yeah, the level 1 modular. Okay, so the picture is as before. I have x of 1. I have my special fiber, and maybe I have a number of supersingular points, and corresponding to that, I have a number of supersingular residue disks. The cusp infinity lies somewhere in the ordinary locus. And then we have this form which is 1 over p plus 1 over convergence, so it converges a little bit further into these disks, where I take away a disk of radius p to the power minus 1 over p plus 1. So it converges on the complement of these disks. Okay? All right. Now, the statement is that there's a set of zeros that I can tell you exactly, and in fact it'll turn out those are all the zeros. So for any k greater than or equal to 0, there are precisely p minus 1 p to the k zeros in that residue disk where the value of r, so it measures how deep into the supersingular locus you are, is given by 1 over p plus 1 minus 1 over nd, some integer which I'll tell you about in a second, times p plus 1 p to the k. Okay, so everything is explicit once I've chosen a k, except this nd. But nd you can just ignore, you can pretend it's 1 or something. Nd in general is a divisor of 12, which is prescribed by the number of automorphisms that your supersingular elliptic curve has. Yeah? So it's a very innocent kind of rescaling factor. In this example, it's equal to 4. Yeah? Okay. So they lie all. So in fact, if I draw a picture of this, just to make it slightly more concrete, what this thing is saying, and maybe also sharpen the statement slightly. How shall I do this? Let's take blue. Let's zoom in. So I'm supposed to pick one of these residue disks. Yeah? So let's pick this one. We have our forbidden region in the middle. So let's make that red. Where our function doesn't converge, but it does converge on the complement. And so what the theorem is saying is that just take any k, and let's start slow. Let's start at the bottom. Maybe there's a number of zeros here, not that many, a little bit into the supersingular locus. And then at the next step, I get slightly more zeros, a little bit further in. And then at the next step, I get, again, exponentially more zeros, a little bit further in. And it sort of will equidistribute all along towards the boundary. That's kind of the picture to have. So we proved that these are the valuations, so this is how deep they lie inside of it. But in fact, our proof shows also an equidistribution along the specific slices that you take of a certain radius. So the number of zeros very nicely equidistributes inside of here. The second part of this theorem is that these are in fact all the zeros. Of this iso integral of the raised to Eisenstein series, with the exception of the cusp infinity, where of course this thing will also vanish. It's periodic. Okay, so I'm almost out of time, so I won't say anything about the proof. The proof again uses sort of p-Adic privileges, and there's one thing maybe that I can say is that these zeros, they're a little annoying at first sight to get your hands on, because they don't occur at any points that we seem to know. They're not CM points or anything like that, as maybe initially one may have hoped. Rather, what these zeros are is they're global points on the modular curve, but they correspond to elliptic curves defined over Q bar, whose p squared torsion has a certain internal symmetry. That's what we see in the proof. So we say actually exactly what those zeros are. But it's a strange kind of symmetry. And it comes out of the observation that, in fact, this Eichler integral, you could write it explicitly as the p-Adic logarithm of some rigid analytic function, which is v of a Hauptmodul divided by the pth power of a Hauptmodul, roughly. And if you do computations in the formal group, which is really the main method by which we achieve this theorem, you will see that there's a certain type of symmetry that the second canonical subgroup of an elliptic curve in this region is allowed to have between its p squared torsion point, which is a little bit strange. And it's a set of elliptic curves that I think I haven't seen before. So it's an interesting set, and because they're not CM points or anything, you rely on explicit calculations in the formal group to prove this theorem. But I think this set, because it's a set of global points that's not CM, it's actually maybe of independent interest to study. Okay, so with that said, maybe that suffices for today. I hope I convinced you that there are some compelling analogies that one can make between mass forms and overconvergent modular forms that go beyond this kind of slope zero subspace, which has been the focus of so much recent work. That also the rest of the spectrum seems to have compelling analogies, most of which seem to be out of reach, but sometimes you can extract some statement that actually p-Adically seems approachable, in fact maybe even more approachable than it was in the Archimedean case, where the zero locus is somewhat harder to get in your hands. So with that said, I think I'll stop, and thanks very much.